Imagine a complex application where hundreds of objects must pass data back and forth simultaneously. Without a master plan for how these memory addresses reference each other, the system eventually collapses under the weight of unsynchronized crosstalk. The Unified Modeling Language, or UML, provides the strict isomorphic representation required to manage this architecture. Isomorphism means there is a direct mathematical equivalence between the visual model and the underlying code. The exact structure of a massive Java codebase can be entirely predicted by evaluating a few simple geometric lines drawn on a page. To read these diagrams, we have to separate the abstract blueprint, the definition of what a thing is, from the physical footprint it eventually occupies in system memory when the program actually runs. If the visual diagram is structurally flawed, the corresponding system memory will inevitably leak or crash. Every box, arrow, and label carries a specific executable consequence. This diagram shows the class node. It is divided into 3 strict compartments: top for class name, middle for attributes, and bottom for operations. Notice the plus, minus, and hash symbols. These visibility adornments act as strict encapsulation boundaries. This slide maps those specific symbols directly to their programmatic equivalents in object-oriented languages. A plus sign creates a public feature, accessible by any client. A minus sign enforces private isolation, and a hash marks a protected feature, accessible only to subclasses. We can contrast that abstract class definition with this diagram, which shows a living instantiated object. You know it is a specific object residing in memory because its identifier is underlined, and its attributes hold concrete values, like a balance of $300. A single named rectangle on a page represents a specific, bounded, and protected footprint in system RAM. Defining an object in isolation is trivial. The true engineering challenge lies in dictating how these disparate units connect and communicate without creating endless loops. This diagram shows an association. An association is the required structural link that holds a reference between 2 different memory addresses, allowing a company object to interact with a person object. This graphic highlights navigation ability. The open arrow pointing from an order to a product is a strict directive dictating data dependency. It translates directly to the order class containing a list of product objects in the code. Order knows exactly where to find its products. The inverse constraint is equally rigid. If there is an X or no arrow pointing back, it means no direct memory reference can legally exist from the product back to the order. The target remains completely blind to its owner. A simple arrowhead physically forces one code file to depend entirely on the compilation and existence of another. Structural links must be tightly constrained. Without limits on how many objects can be attached to a connection, an application could attempt infinite memory allocation. This table presents the exact notation matrix used to define multiplicity rules across an association, specifying the exact number of objects that can participate at any point in time. This diagram applies those mathematical constraints to a real domain scenario. Notice the connection between a person and a bank account, which is labeled with a 0 ... meaning 0 to many. In Java memory allocation, that theoretical asterisk translates directly into a dynamic array list. The system must instantiate a data structure capable of expanding on demand to hold anywhere from 0 to millions of references. We can contrast this dynamic scaling with fixed multiplicity, like the strict 1 above the company class. Exact bounds force fixed array allocations, locking in the exact amount of RAM required upon initialization. A single asterisk placed on a diagram commits the running application to dynamic memory overhead and active list management.
This diagram presents a specific modeling dilemma. When a person is employed by a company, they receive a salary. But recording that salary becomes problematic if the person holds multiple jobs at different companies simultaneously. If the salary attribute is placed on the person object, taking a second job would overwrite the previous data, destroying their employment history. If the salary is placed on the company object instead, the system would apply one single salary uniformly to every employee in the database. This diagram introduces the association class as the architectural solution. It is used when business logic and data belong to the relationship itself, rather than to a single entity on either end. The dashed line connecting to the job class dictates that the connection must be instantiated as its own dedicated object in memory. Every time a person is linked to a company, a new unique job object is born to securely hold that specific salary. Recognizing when an invisible relationship requires physical memory space prevents data corruption. As a system scales, iterating through a massive, unorganized list just to find one specific object reference creates a severe performance bottleneck. To solve this, UML uses a qualified association. It introduces a mechanism to extract a unique identifier, like a player's nickname, for immediate direct lookup. Standard lists fail this specific architectural constraint, requiring scanning every element one by one until a match is found. This visual qualifier explicitly mandates a key-value data structure, guaranteeing O of 1 time complexity by organizing memory references into a highly optimized map. However, this creates a bidirectional mapping danger. Both the league and the player must maintain references to each other, meaning both sides of the map must be perfectly synchronized during every transaction, or the system state will fracture. Adding a tiny qualifier box to a diagram rewrites the underlying code from a slow, linear array to a high-performance hash map. Now we can transition from mapping concrete object connections to defining abstract conceptual promises between completely decoupled systems. This diagram displays interface notation. The ball and socket visualizes service supply and demand, establishing a specification of a named contract offered by a class. This diagram expands on that relationship. It differentiates between a provided interface, where a classifier supplies the defined operations, and a required interface, which demands those exact operations to function. This slide shows the Java execution. The dashed realization arrow forces the class to implement every promised method. If it fails to provide the exact method specified in the interface, the compiler rejects the code entirely. These interfaces act as strict legal contracts. They allow massive, disconnected engineering teams to compile code against a shared promise, long before the specific internal logic is ever built. We can prove the validity of this entire system by systematically deducing a complex architecture from raw, unstructured business rules. If a commercial bike hire system requires us to keep a record of a hire transaction, we know that the transaction belongs to neither the customer alone nor the bike alone. It demands an association class. When the requirements state a customer gets one unified receipt for multiple bikes, we instantly extract the multiplicity constraint, a one-to-many relationship, mapping a single receipt instance to an array of bike references. What was previously ambiguous human language is now a safely executable, rigorously defined structure. Software engineering functions through the mathematical translation of business requirements into executable structures. In this paradigm, architecture dictates the limits of the physical system.